How do we actually tell the story of a complex system? I mean, how do we describe the intricate dance of events, some happening in a strict order, while others are happening all at once? Well, to do that, you need special languages, really powerful forms of logic. So today, we're going to dive into two of them, LTL and regular LTL. Let's see how they work.
Okay, so here's our game plan. First up, we'll get to know the classic storyteller, LTL. That's going to be our baseline. Then we'll meet two, let's call them advanced narrators, LTRL, who's a specialist in parallel worlds, and RLTL, a master of complex patterns. After that, we'll put them head-to-head to see how they really stack up, and finally, we'll figure out when you'd call on each one to tell your system's story.
All right, let's start with our foundation, standard linear temporal logic, or just LTL for short. And as the slide says, this is our linear storyteller. Think of it as the most straightforward, by-the-book narrator you can possibly imagine.
So the whole idea behind LTL is that time moves in one straight, unwavering line. Period. It's built to reason about a single, infinite sequence of events, where there's always a crystal clear before and after for absolutely everything that happens. No ambiguity.
A simple process like this is LTL's bread and butter. First, a request gets sent. Then, and only after that, it gets processed. And finally, a response is received. See? It's a simple, step-by-step story where one thing just follows the next in a super strict, predictable order.
Yeah, this slide just nails it. LTL sees the entire universe as a single reel of film, playing out frame by frame in a rigid sequence. But what happens when the world isn't a single movie? What if you've got multiple storylines all happening at the exact same time? And that brings us to our first major upgrade. I mean, think about distributed systems, the internet, cloud computing, even the processor in your phone. Events are constantly happening in parallel. This is the exact problem LTRL was born to solve. This slide shows the huge shift in thinking here. On the left, LTL forces everything into one single timeline. But LTR, on the right, it embraces what's called a partial order. It basically just says, look, if two events are independent, I honestly don't care which one came first. The only thing that matters is the chain of cause and effect. So the formal name is a mouthful, Linear Temporal Logic over Traces, or LTRL. It's built on this mathematical concept called Mazurkiewicz traces, which, look, it's really just a formal way to model these partial orders we were talking about. It lets us capture the true essence of what a distributed system is doing without jamming it into some artificial linear sequence.
So why is this so powerful? Well, it's designed from the ground up for concurrency, and it zeroes in on causality. It's also what's called expressively complete. What that really means is it's powerful enough to describe any property of these concurrent systems that you could describe with more complex, low-level logic. And that ability is absolutely crucial for verifying modern systems. But, and this is a huge but, that power comes at a staggering price. The computational complexity of checking these properties is formally known as non-elementary. And that means it's so mind-bogglingly expensive that it's beyond exponential, it's even beyond double exponential. It's a computational nightmare. So while LTRL is incredibly powerful, you definitely pay for it. Okay, let's pivot. What if your problem isn't concurrency at all, but instead it's describing these incredibly complex repeating patterns, even if they're on a single timeline? Well, for that job, we need a totally different kind of master storyteller. Meet regular linear temporal logic, or RLTL. Now, this is an extension of our original LTL, but it comes with a superpower. It can use regular expressions, and this allows it to describe any omega regular property. You can just think of this as the entire universe of repeating patterns that a computer could possibly recognize over time. Now, this is the amazing part. RLTL is strictly more powerful than standard LTL. It can describe things LTL just can't even touch. It captures every possible repeating pattern, and yet, and this is incredible, its computational cost doesn't go up at all. Checking RLTL properties is what's called PS-space complete, which for us is the exact same difficulty as basic LTL. You get all this extra power, basically for free. So what we have here are two really powerful extensions to LTL, and each one solves a very different kind of problem. Let's put them side by side and really see how they compare. This table sums it all up perfectly. LTRL is all about concurrency, using partial orders to model time. It's incredibly expressive, but its complexity is non-elementary, which is code for very, very high. Then you have RLTL. It focuses on capturing all regular patterns, but on a linear timeline. It's as expressive as you can possibly get for those patterns, and its complexity is a much more manageable p-space complete. Honestly, if you remember just one thing from this, make it this brilliant analogy right here. LTR is the storyteller you hire to describe a huge distributed organization. It gets that what matters is who caused what, not the exact minute-by-minute order of every single little thing. RLTL, on the other hand, is the master grammarian who can describe any repeating plot you can dream of, no matter how complex, as long as it happens in a single narrative. And this brings us right to the final practical question. Given these two specialists, how do you actually choose which one to hire for the job?
The choice actually breaks down pretty clearly. If the absolute heart of your problem is true concurrency, independent actions happening in parallel where causality is king, then you need LTRL, and you just have to be ready for that heavy computational cost. But if your challenge is to describe some intricate repeating sequence on a linear timeline, RLTRL gives you incredible power without that computational penalty. So at the end of the day, the crucial takeaway is this. There is no single best logic. It's not about that at all. Like any good toolkit, it's about picking the right tool, the right storyteller for the specific story your system needs to tell. And that leaves us with a really fascinating thought. I mean, our systems are only getting more distributed, more parallel, and their behaviors are getting way more complex. The stories are getting a lot harder to tell. So the real question isn't just which logic we use today. It's what new kinds of storytellers will we need to invent for the systems of tomorrow.